Okay, so let's dive into this. When you picture an old building, what often comes to mind? Probably a bit drafty, maybe struggling with those heating and cooling bills.
Yeah, that's the common image, isn't it? Old and drafty.
Right. But what if I told you that some of the most ingenious secrets to future energy efficiency have actually been hiding, in plain sight, tucked away behind those very facades?
That's a great point.
Today, we're taking a deep dive into how buildings breathe. We're exploring everything from, well, ancient construction wisdom to the really cutting-edge modern solutions that help us save energy and, stay comfortable.
That's exactly it. And we'll be pulling insights from a fascinating stack of sources today.
Mm.
Detailed architectural research, some deep discussions among building professionals, and really practical insights from design firms, too.
Mm-hmm.
Our mission here is to sort of extract the most important nuggets of knowledge, helping you understand why some incredibly smart building practices maybe fell out of favor, what we're doing now, and what surprising lessons from the past are shaping the future of sustainable living.
Sounds good.
Yeah, you're going to discover how we can be truly well-informed about making our homes greener, more comfortable, often with a genuine aha moment, I think.
I like the sound of that. So this idea that old buildings might actually be climate heroes, it feels counterintuitive, doesn't it? It certainly challenges a lot of our modern assumptions.
It absolutely does,
Mm.
especially when we're so used to just labeling them as old and inefficient or, like you said, drafty. But architect Carl Elefante coined a really powerful phrase. The greenest building is one that is already built.
Huh, okay.
And these historic buildings, typically over 50 years old, they often possess inherent energy-efficient qualities that we frequently overlook. Think about it. They relied heavily on what we now call passive design principles.
Right.
This means taking advantage of natural daylighting, carefully orienting the building to the sun, using smart ventilation strategies,
Right.
all to reduce the need for mechanical heating and cooling. They were built to work with nature, not fight against it.
So they were designed to be resilient, yeah, even before we really had that term, maybe.
Exactly. They were also constructed with passive survivability in mind. That means they could maintain, reasonably comfortable conditions even during power outages because they weren't entirely reliant on plugging things in.
Makes sense.
Beyond that, many older buildings still standing today, they were built with more durable, longer-lasting, traditional materials.
Hmm.
And here's another interesting point our sources highlight. They were often more compact.
Oh, right. Smaller houses.
Yeah, much smaller on average. Between 1970 and 2015, average U.S. home sizes increased by a staggering 57%.
Wow. 57%.
Yep, and this massive growth actually wiped out many of the energy efficiency gains made per square foot during that same period.
That's incredible. So we got more efficient per foot, but built so much bigger it didn't matter overall.
Pretty much cancel it out, yeah. And when we look at this through a life cycle assessment approach, which evaluates a building's environmental impact from, raw materials all the way to demolition studies show remodeling historic buildings uses significantly less energy than entirely new construction. Doesn't matter the building type or climate, really.
That initial energy hit of new construction is huge then.
It's massive. Think about all the materials, transport, construction energy. Even if a brand new building is, say, 30% more efficient to operate, it can take up to 80 years, 80, to offset the negative climate impacts of just building in the first place.
80 years. That puts things in perspective.
It's a really profound thought, isn't it?
So here's where this surprising paradox comes in. Despite this inherent efficiency, you've got this huge chunk of our housing stock, about 38% of housing units over 50 years old, often dismissed as, part of the climate solution.
Right.
And what's kind of worse, current regulations can actually make things harder inadvertently.
They really can. And this is where it gets, frustrating. Congress formally declared way back in 1966 with the National Historic Preservation Act that preserving historic heritage also maintained its energy benefits. They saw it then.
Okay, so they knew.
They did. But the modern regulatory framework often overlooks this. Historic buildings, they're frequently exempt from modern energy conservation codes like the IECC or HHRE standards that apply to new construction.
Why exempt them?
Well, the rationale often states that compliance would threaten, degrade, or destroy the historic form, fabric, or function of the building.
So a law designed to protect the building's character can actually block efficiency upgrades, that sounds like.
All right.
Yeah, a classic case of good intentions maybe creating unintended
It
consequences.
absolutely can be. And beyond just those energy codes, you've got the Secretary of the Interior standards for the treatment of historic properties.
Mhm.
These standards, particularly for rehabilitation, which is meant to be the most flexible approach, they often don't even explicitly mention energy efficiency.
Yes.
Yeah. And sometimes they can even thwart efforts. We see this in real-world examples that came up in the research.
Like what?
Okay, take the Swift factory in Hartford, Connecticut, a $34 million rehab project. The developer proposed putting insulation on the inside, no visual impact on the exterior, and using these precast concrete sills with a thermal break. That's basically just a material that stops heat from easily passing through, makes the building way more efficient.
Sounds sensible, smart, even.
You'd think so.
Yeah.
But both ideas were rejected by the National Park Service. They claimed the interior insulation would detract from historic character, even though you couldn't see it, and the thermal break was inconsistent with standards.
So what happened?
It added about $250,000 to the project costs and, ironically, reduced its energy efficiency, which means higher energy bills and less comfortable spaces for the people using it.
Oh, that's infuriating, actually. It sounds like they prioritized a very specific, maybe narrow interpretation of historic character over actual function and sustainability.
That's often how it plays out. And then there's the Hotel Marcel in New Haven. This is a huge, ambitious project, $50 million, aiming for net zero, passive house certified hotel. Really forward-thinking.
Wow. Okay.
The developer faced 14 months of delays. 14 months. And considerable extra costs just to get triple glazed windows approved. The NPS also rejected these things called light wells that would bring natural light into the corridors, limiting them just to the guest rooms.
Why? Was there a preservation reason?
Apparently not an obvious one. These rejections just seem to undermine the energy efficiency goals without any clear preservation benefit. It just created hurdles.
So the really powerful, almost, infuriating insight from these cases is that the very laws designed to protect our heritage can, in practice, create this barrier. They stop these buildings from becoming the climate solutions they could be.
It's a fundamental disconnect.
Yeah.
It actively prevents them from becoming what they inherently could be sometimes.
Right.
Okay, shifting gears a bit. Given
Yeah.
the durability you mentioned, the long-lasting nature of traditional materials, it raises a big question. Why aren't we seeing materials like stone, or even things like adobe, used more widely for new construction today?
Yeah, that's a really good question. It's complex and often gets boiled down to just cost, but there's a lot more to it.
Okay.
For one, stone itself is harder to get, harder to transport, and much harder to work with. It requires highly skilled artisans, masons, and those skills are rarer now and therefore more expensive.
Right, labor costs.
Big time. And building with stone takes significantly longer. We're talking months versus maybe weeks for a standard wood frame house. That really impacts project timelines and the overall bottom line for developers.
So it's a massive time and labor investment that modern construction, which is often focused on speed and efficiency of process, tries to minimize.
Absolutely. And then modern construction has different requirements built in. For the interior spaces, we need cavities, right? For insulation, plumbing pipes, electrical wiring, all that stuff.
A solid stone wall doesn't naturally provide that. So often, if you see stone today, it's actually just a facade, a thin layer over a standard wood-framed wall behind it.
Ah, okay. So it's not structural stone usually?
Not usually in residential, no. Also, stone itself has a pretty low R value. That's just the measure of how well it insulates, how much it resists heat flow.
Right.
So it's not a great insulator on its own. To properly insulate a true stone wall, you often have to either clad the exterior, which hides the beautiful stone, or you build out the interior with framing, called furring out. But that eats into your usable square footage, and if you don't do it right, you can trap moisture.
Moisture. Yeah, that sounds like a problem with stone.
It can be.
Yeah.
Stone can soak up water, feel damp inside. And worse, if water vapor condenses inside the wall because of temperature differences, it can freeze and expand in colder climates, damaging the stone and the mortar over time. It needs careful management.
Okay. What about the thermal mass idea? Doesn't thick stone help keep temperatures stable?
It does, yeah. Thick stone walls have excellent thermal mass. They absorb heat during the day and release it slowly at night. But that's most effective in hot, arid climates. Think deserts.
Okay.
In hot, humid climates, you actually want to minimize that thermal mass because it just holds onto the heat and humidity. So climate matters a lot.
And what about stability, like earthquakes?
Big factor. Unreinforced masonry, Traditional stone, brick,
Mm.
adobe performs really poorly in earthquakes. It needs steel reinforcement, which adds complexity and cost. And even that steel can degrade over time, sometimes in less than 100 years. So in seismically active areas, which is a lot of the U.S.,
Yeah.
it's a major concern.
Uh,
Plus, just the thickness. Stone walls are thick. That means less usable interior floor space on the same size plot compared to thinner modern wall systems.
Gotcha.
So the takeaway isn't that these ancient materials are bad or anything. It's that fitting them into modern construction faces these really complex hurdles: labor, cost, insulation, moisture, seismic issues, space. It's all package of trade-offs.
Makes sense. It's not just a simple cost answer, then. It's this complex interplay of the material itself, the climate, modern building needs, labor. So you mentioned sources, looking at specific examples. What about that Gaodang village in China? What does that teach us about the continued relevance of stone, maybe in specific contexts?
Right. Gaoding Village in Guizhou, China.
Mm-hmm.
It's a fascinating example of this ancient wisdom still in action. For over 600 years, almost all the buildings there have been meticulously constructed with locally sourced stone.
600 years, wow.
Yeah, they used local limestone or dolomitic limestone, stuff that was easily quarried right nearby. It was almost like a mining and construction simultaneously approach, which saved a ton on labor and transport costs.
Smart, using what's right there.
Exactly. And those thick stone walls provide natural insulation, regulating the indoor temperatures. What's also really interesting is how the village layout itself wasn't just on a grid. It adapted to the hilly terrain, the karst mountains there. It emphasized harmony with nature, but also strategic defense. Yeah, the layout considered that too. It was this blend of practicality, defense, and even cultural principles like feng shui influencing where they chose to build. Very holistic.
So the wisdom of using local, durable materials for thermal properties, stability, that's clear. But given all the complexities you just described for modern builds, how do we get that balance today? How do we save energy and stay comfortable without necessarily building solid stone walls everywhere?
Right, that's the key question, isn't it? If building entirely new stone houses isn't practical for most of us today, what are architects and builders doing to ensure energy savings and comfort? And this is where understanding how a building breathes, how it interacts with its environment, becomes really critical.
Okay.
Our deep dive into the sources on natural ventilation and passive solar design really highlights this. It's a fascinating blend of that ancient wisdom with modern technology and understanding.
Natural ventilation, just opening windows.
Well, yeah, but it's more strategic than that. It's humanity's oldest cooling strategy, basically harnessing wind and buoyancy. You've got wind-driven ventilation, which creates pressure differences across the building, pulling air through open windows.
Okay.
And then there's the stack effect. It's also called thermal buoyancy or the chimney effect.
Yeah.
Simple physics. Warm air is less dense, so it rises. If you provide high openings, it escapes. And that naturally draws cooler, denser air in from lower openings.
Ah, like a chimney draws smoke up.
Exactly the same principle. It's particularly effective for something called night purging or night flushing. In climates where it cools down significantly at night, what we call a large diurnal temperature swing, you can open windows strategically overnight to flush out the heat buildup during the day and cool down the building's mass.
So literally opening a window upstairs and one downstairs, letting physics do the cooling work overnight.
That's the core idea, yeah. And the benefits are pretty significant. Our sources suggest it can reduce cooling costs by anywhere from 10 to 30%.
That's quite a bit.
It is. And think about air quality. Indoor air is often 2 to 5 times more polluted than outdoor air. Natural ventilation dramatically improves that. Plus, just the feeling of air movement can make a space feel up to 5 degrees Fahrenheit cooler. Even if the actual air temperature hasn't changed much, it improves comfort.
Yeah, that breeze feels good.
It does. There are health benefits too, reducing pollutants, maybe even improving sleep quality. And of course, it lowers a home's carbon footprint. Air conditioning in the U.S. alone emits something like 117 million metric tons of CO2 annually.
Wow.
Using less AC makes a difference. Plus, it increases resilience. If the power goes out on a hot day, you still have a way to cool down. And there's that psychological connection to the outdoors too.
Okay, so what are the key things to get right? The principles.
Well, architects like Hutter architects, mentioned in our sources, lay out some core principles. Orientation is key. Aligning the home's longer sides perpendicular to the prevailing summer winds, if possible. Building width matters, ideally under 45 feet for good cross ventilation. Bigger homes might need things like internal courtyards or atria to help.
Okay.
Dual openings are crucial. Each room, ideally, should have at least 2 openings,
Hmm.
preferably on opposite or adjacent walls, to let air flow through. Vertical separation helps too, inlets low, outlets high, to really maximize that stack effect we talked about.
Right, get the hot air rising out.
Exactly. And you need unobstructed interior flow. Open floor plans help, or things like transom windows above interior doors can allow air to move even when doors are closed.
So the windows aren't just for views anymore. They're like vital parts of the home's lungs strategically placed.
That's a great way to put it. Yeah. Window sizing and placement are critical. The total operable window area, the part you can actually open, should be at least 5% of the floor area. Maybe 10% if you only have openings on one side of a room. And the type of window matters too. Casement windows that crank out, awning windows, double hung where both sashes move, clerestory windows up high. Architects choose these strategically for airflow.
Got it. And beyond just ventilation.
Passive solar design is the other huge piece. Getting sunlight in during the winter, keeping it out in the summer. Southern-facing windows in the northern hemisphere are absolutely key for absorbing the low winter sun's heat. Get the orientation right, ideally within 5 to 15 degrees of true south, and sources say you could reduce heating and cooling costs by as much as 85%.
85%. That's massive.
It's potentially huge, yeah. But you need proper overhangs, too. Designed just right, they block the high summer sun from overheating the house, but they let that lower winter sun stream in.
Clever geometry.
It is. And finally, thermal mass. Using dense materials, concrete, brick, stone, maybe even adobe floors or walls strategically placed where they can absorb that winter sun heat or the coolness from night flushing and then release it slowly. It helps stabilize the indoor temperature.
This all sounds like working with nature, like you said, rather than just battling it with mechanical systems. But are these strategies really one size fits all? Surely it depends on the climate. And what about the cost? Does this add a lot?
No, absolutely. It's definitely not one size fits all. Climate responsive design is the name of the game. What works in Arizona won't work in Florida or here in Chicago.
Right.
So for instance, in hot, dry climates, the focus is really on that night flushing and using high thermal mass to store the nighttime coolness. Maybe features like wind towers to catch breezes, but in hot, humid climates, you want to maximize cross-ventilation constantly, maybe lift the living spaces up off the ground on stilts. Definitely use ceiling fans. Minimizing thermal mass is often better there.
And cold climates, like us.
Yeah, for cold climates like Chicago, you might use something called pulse ventilation in winter opening windows briefly, just to exchange air without losing too much heat. And making sure everything seals up really tight when you're not ventilating is critical to conserve energy.
Makes sense. Are there specific architectural features that help with this airflow?
Definitely. Things like louvers, screens, operable skylights, which are fantastic outlets for rising warm air. Courtyards and atria can create microclimates and drive ventilation, even on really tight urban lots. Green roofs are great. They insulate, but they also cool the air around them through evapotranspiration. Even water features like a small courtyard fountain or a water wall can provide evaporative cooling, dropping the nearby air temperature by maybe 3 or 4 degrees Fahrenheit.
Water features for cooling. Interesting.
Yeah. And there are even concepts like the double roof house, where you create an air gap between 2 roof layers specifically for ventilation. Lots of clever adaptations.
Okay, but the cost. Are we talking high-end custom builds only?
That's the really encouraging part. The sources suggest that planning for natural ventilation right from the start adds very little to the actual construction costs. Typically less than 2% of the overall budget.
Less than 2%. Seriously.
Yep. For potentially substantial cooling energy reductions, remember that 10–30% range.
Yeah.
So the upfront investment is often very reasonable for the long-term gains in both comfort and energy savings. It's more about smart design than expensive tech.
Okay, that's good to hear. So these strategies are effective, clearly cost-effective if planned early. But what about situations where natural ventilation just isn't quite enough? You know, heat waves or really humid days. Where do mechanical systems still fit in?
That's a really important point.
Mm-hmm.
Natural ventilation isn't a magic bullet for every single hour of the year. That's where hybrid solutions or mixed-mode systems come in. The idea is to blend the best of both natural and mechanical systems for optimal comfort and efficiency.
Mixed mode. How does that work?
Well, mixed-mode ventilation often uses smart controls. Sensors monitor indoor-outdoor temperature, humidity, maybe even air quality.
Yeah.
The system automatically shifts between natural ventilation, opening windows automatically when conditions are right, and turning on the mechanical cooling or heating only when needed.
Ah, so it optimizes constantly.
Exactly. Takes the guesswork out of it. Whole house fans are another great tool in the hybrid approach. They're pretty energy efficient, and they work by pulling air through the house when windows are open. They use maybe only 10% of the energy of a central AC unit. Really great for that night purging we talked about.
Right, actively pulling the cool air through.
Yep. And don't underestimate the humble ceiling fan. Simple, cost-effective. They don't actually cool the air, but the air movement across your skin makes you feel much cooler, maybe by up to 5 degrees Fahrenheit. Allows you to set the thermostat a bit higher if you do need the AC.
Good point. What about fancier tech?
There are things like smart window actuators. These can automatically open and close windows based on those preset conditions or schedules, getting more common in commercial buildings, maybe starting to see them in homes too.
So mechanical systems aren't obsolete, they're just used more strategically, maybe less often. When are they really essential?
That's the perfect way to put it. They become the backup, the support system. They're crucial during extreme heat waves, obviously, or in consistently humid areas where you really need dehumidification, which natural ventilation alone can't always provide. Also important for people with severe allergies or asthma who need highly filtered air, or even in specific rooms with high internal heat loads, like a home office packed with electronics.
Right.
The real art is in designing flexible systems that prioritize the natural strategies first, saving the energy-intensive mechanical systems for when they're truly necessary to maintain comfort or health.
And you mentioned water earlier,
Yeah.
and even plants. It feels like bringing those elements in is also part of this holistic approach to comfort, almost timeless.
They really are. Historically, water was so integral to human gathering spots and comfort. Think ancient Roman baths or just town squares built around fountains. Architects are now reintegrating water features, channels, water walls, ponds, not just because they look nice, but for their tangible environmental benefits.
The evaporative cooling effect.
Exactly. It improves thermal comfort in the immediate surroundings, creating these little microclimates, and that can significantly reduce the load on mechanical cooling systems. And then green walls, vertical gardens, basically.
Yeah, you see those more now?
They bring nature right indoors, which is great psychologically. But they also improve air quality by absorbing CO2 and releasing oxygen. They help lower indoor temperatures through shading and evapotranspiration, and they give you maximum green space using minimal floor area. It hits comfort, energy savings, and well-being.
It really does seem like these examples tie everything together. Timeless wisdom, thoughtful modern design, a bit of tech, all leading to healthier, more comfortable, and definitely more energy efficient living spaces. Wow, what a journey we've taken. We've seen how these, often dismissed historic buildings actually hold critical lessons for our climate future, and how modern design is actively rediscovering and integrating these passive strategies. It really is about designing buildings that breathe and adapt, isn't it? Instead of just sealing them off from the world.
Indeed. And this confluence of past and present, it just reinforces that sustainable practices aren't always radical innovations. Often they're a return to some really pragmatic genius that maybe we forgot for a while. The goal becomes minimizing that mechanical intervention, right? Saving those systems for when they're truly needed, optimizing for comfort and efficiency without just running the AC constantly.
So, maybe a final thought for everyone listening. As you think about your own living space, or your workspace, or perhaps your next project, maybe consider this. How can you foster a greater connection with your environment by letting your space breathe more naturally? What simple strategic changes might you be able to make? How can you harness some of that power of passive design to reduce your energy footprint, enhance your own comfort, and maybe rediscover some of that timeless wisdom that's embedded in the very fabric of our built world?